Chapter 15, Quantum Translation, Section 15.6, The Tunneling Effect. When the energy barrier for the particle in the box is finite, the particle may appear outside the box, even if its energy is lower than the energy barrier, denoted by V0. V0 is a constant. This is called quantum tunneling. Outside the box, we have the shown equation. Over here, we have kinetic energy operator applied to psi. This is the potential energy applied to psi. The sum is h psi. H psi equals E psi. Now we can solve this differential equation. The second derivative of psi is equal to 2m V0 minus E over h bar squared times psi. The second derivative of a function is itself multiplied by a constant. So naturally, we think of exponential functions. The solution is indeed either e to the power of kappa x or e to the power of negative kappa x. A is just the normalization factor. This kappa is the square root of 2m times V0 minus E over h bar squared. Or we can write this kappa as the square root of 2m times V0 minus E, and then divided by h bar. This h bar is outside the square root. Because V0 is greater than E, kappa is real. It's a real number because mass is positive. If V0 is greater than E, this is positive. The square root of a positive number is a real number. So kappa is a positive real number as long as V0 is greater than E. Because the wave function must be finite, we'll choose this exponential function, e to the power of negative kappa x, where we define x as the tunneling distance between the particle outside and its nearest boundary. So x is always positive. It's the distance between the particle, for example outside here, the distance between the particle and the nearest boundary. We need this negative sign to make sure the wave function is finite. Now, since the total energy of the particle may be lower than its potential energy, we name this phenomenon quantum tunneling. Why? Because kinetic energy is equal to total energy minus potential energy. And if the total energy is less than potential energy, that means the kinetic energy of the particle outside the box is negative. It's a classically forbidden region. The tunneling wave function is e to the power of negative kappa x times the normalization factor A. X is the tunneling distance between the particle outside the box and the nearest boundary of the box. X is always positive. Kappa is also positive when V0 is greater than E. But again, when V0 is greater than E, that means the kinetic energy of the particle is negative, and it's so-called the classically forbidden region. Now, since psi is A times e to the power of negative kappa x, the tunneling probability density is psi squared. It's A squared times e to the power of negative 2 kappa x. Apparently, this function decays exponentially as x increases. When x increases, psi squared decreases. The rate of the decay of the tunneling probability depends on the magnitude of this kappa. And again, kappa is the square root of 2m times V0 minus E, and then divided by h bar. If kappa is large, this exponential function decreases rapidly. If kappa is small, this exponential function decays slowly. We observe more significant tunneling over a longer distance. Now, let's analyze this expression. When the mass of the particle is small, that means when the m is small, and also when v0 minus c is small, then kappa is small. When kappa is small, the tunneling probability e to the power of negative 2 kappa x decays slower as x increases. However, when the mass is large, and when the difference between v0 and e is large, then kappa is larger. The tunneling probability decays more rapidly. Again, when kappa is large, this exponential function decreases very rapidly. In summary, it's more likely to observe lighter particles, such as electrons, tunneling through a shorter distance, such as 1 angstrom. Meanwhile, it's highly unlikely to observe heavier particles, such as protons, tunneling through a longer distance. The mass of a proton is 1800 times the mass of an electron. So over here, they differ significantly. Now let's look at several examples in which a proton versus an electron tunnels through 1 angstrom distance versus 10 angstroms distance, with v0 minus e being 1 electron volt versus 10 electron volts. 1 angstrom is 10 to the power of negative 10 meters. 1 electron volt is 1.6 times 10 to the power of negative 19 joules. First, let's look at electrons. When x is just 1 angstrom, that means the tunneling distance is only 1 angstrom. And when v0 minus e is only 1 electron volt, that means the total energy is only 1 electron volt lower than the energy barrier. We can compute this kappa this way. We plug in all the numbers, 2 times the mass of the electron times v0 minus e, and then over h bar. It's about 5 billion per meter. Since the probability density is psi squared, the probability of finding the particle drops to this much after a tunneling distance of x. When x is 1 angstrom, we plug in the value of x and kappa. Kappa is 5 billion per meter. X, the distance of tunneling, is 1 angstrom. We plug in all the numbers, we get e to the power of negative 1. That's 0.36. So for an electron to tunnel through a barrier that's higher than the total energy by 1 electron volt, it's entirely possible. There's 36% chance to see this electron appearing just 1 angstrom outside the box, even if its kinetic energy on paper is negative. The kinetic energy of this particle outside the box with 1 angstrom tunneling distance is, over here you can see, it's negative 1 electron volt. So potential energy minus total energy is 1 electron volt. Therefore, kinetic energy is negative 1 electron volt. And there's this much chance of observing that electron with negative kinetic energy. However, when the tunneling distance is longer, well, the tunneling effect is smaller. It's just we plug in a longer distance here. Instead of e to the power of negative 1, we have e to the power of negative 10. Now this is so much smaller. It's about 10 to the power of negative 5. The tunneling probability drops rapidly as the tunneling distance increases. Now, what if the total energy is much lower than the potential energy? Let's say V0 minus E is now 10 electron volts. So actually, this means the kinetic energy is negative 10 electron volt. We again plug in all the numbers. We compute kappa again. the square root of 2 times the mass of the electron times 10 electron volt, and then over h bar, we have 16 billion per meter. We use 1 angstrom here, and we have e to the power of -3. Still, we have a decent probability, but this is much smaller than this one already. This is 0.36, this is 0.039. Now, what if the tunneling distance is 10 angstroms? Well, again, we plug in all the numbers. This -3 becomes -30. Minus 3.24 becomes minus 32.4. And over here, it's 10 to the power of -15. This is negligible. So the tunneling probability is smaller when V0 minus C becomes larger. So it's actually possible to have a negative kinetic energy for the particle appearing outside the box, but it cannot be too negative. It's difficult to be too negative. A little negative is fine, a short tunneling distance is fine, but a long distance and a very negative kinetic energy results in a very small tunneling probability. When do we observe significant tunneling? Well, when E is fairly close to V0. E can be less than V0, but not that much smaller. And also, when the tunneling distance is fairly small, we observe a larger tunneling probability. Now let's look at several examples for protons. For protons, we use the same parameters for the tunneling distance and the difference between V0 and E. We compute the kappa again. This time, well, this kappa is really large. And why is that? Because the mass is now 1800 times larger than the mass of an electron. So we're going to plug in all the numbers. Over here, it's actually about 219 billion per meter. Since the probability density is psi squared, then we can compute the tunneling probability using e to the power of -2 kappa x. We plug in all the numbers. We have e to the power of -44, and that's 9 times 10 to the power of -20. Very small number. Even though V0 minus C is only 1 electron volt, the tunneling distance is also only 1 angstrom. But because the mass of a proton is so much heavier than that of an electron, the tunneling probability of a proton is so much smaller than that of an electron. We can also plug in some other values for the tunneling distance. For example, 10 angstroms, and then we get 10 to the power of -191. Alright, so that means this is not going to be observed. We will not observe a proton tunnel through a barrier with this much distance and this much difference between energy and potential energy, because this number is just too small. We have a table of the tunneling probability here. Those are computed with this equation, e to the power of -2 kappa x. Kappa is the square root of 2m multiplied by V0 minus E. On the bottom, we have h bar. X is the tunneling distance. And again, we did 8 calculations, 4 for electrons, 4 for protons. The tunneling distance can be 1 angstrom versus 10 angstroms. This V0 minus E can be 1 electron volt or 10 electron volts. And again, V0 minus E is just negative kinetic energy of the particle. Alright, we plug in all the numbers, we got all those probabilities, and you can see, well, for the protons, all those numbers are really small. But for electrons, if you just tunnel through 1 angstrom distance, and if the energy barrier is only 1 electron volt, well, we have a decent chance seeing tunneling. What if the barrier goes up to 10 electron volt? Still, 0.04, not too bad. What if the tunneling distance becomes 10 angstroms? Now it's fairly hard. It's about 10 to the power of -5. What if the distance is 10 angstroms, the barrier is also 10 electron volt? Well, the tunneling of the electron also becomes negligible. Well, you may ask, can we actually observe the tunneling of proton at all because this number is so small? Well, it's possible as long as we reduce this number or this number. So either way, if we have, for example, a much smaller number here than 1, or a much smaller number than 1 here, and then we will be able to observe a much more significant tunneling of a proton. The idea is to make kappa small. We want to make kappa small to observe more significant tunneling. And also, when x is small, the tunneling probability is significant. When x is large, the tunneling probability is small. Again, we'll analyze the tunneling effect, its prevalence, and more easily observed for light particles, such as electrons, with a short tunneling distance, such as a few angstroms. So it's really easy to see the tunneling of electrons over a few angstroms. Tunneling effects can be observed also for atoms or molecules, only if the tunneling distance is very small or this V0 minus E is extremely small. So ideally, we want both a small tunneling distance and a small V0 minus E to observe the tunneling of a heavy particle, such as a proton or an atom or a molecule. An interesting example of quantum tunneling is the tunneling of the electron in a simple hydrogen atom. The wave function of the 1s electron is e to the power of -r. N is simply the normalization factor. R is the distance between the electron and the nucleus. We will study the solutions to the Schrödinger equation of the hydrogen atom later, but for now, let's look at this wave function. The total energy of this 1s electron is -1/2 atomic unit. 1 atomic unit is 4 times 10 to the power of -18 joules. So -1/2 atomic unit is the energy of that 1s electron. The potential energy of the electron is -1/r atomic unit, and r is the distance between the electron and the nucleus in the atomic unit of length. 1 atomic unit length is 0.529 angstroms. Again, we'll learn this a bit later when we solve the Schrödinger equation for the hydrogen atom. Now, it is possible for the 1s electron to appear in a region that's more than 2 atomic units lengths away from the nucleus. And in that region, well, the kinetic energy is the total energy minus the potential energy, which means it's -1/2 minus -1/r. And minus -1/r is plus 1/r. Now, this is the expression for the kinetic energy of the 1s electron of the hydrogen atom. What if this r is greater than 2 atomic units? Now we have a negative kinetic energy. So we can also observe the tunneling effect in a hydrogen atom. It's just prevalent and easily observed for light particles such as electrons. In general, the valence electrons are less attracted to the nucleus than the core electrons. So it's easier to observe the tunneling effects of the valence electrons. The energy it takes to remove a valence electron from an atom or molecule is just much smaller than the amount of energy to remove a core electron. And this is why chemical bonds are always formed by the overlapping of valence electrons, never core electrons. The interference between the core electrons is almost always negligible, only because, again, it's extremely difficult to find a core electron far away from the nucleus, far enough to overlap with another core electron in another atom. So chemists care about valence electrons and the overlap of valence electrons. Chemists do not care about core electrons, and the overlap between core electrons is always negligible.